Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. The other day I had the pleasure of being on with Nathan Oakley and the Flat Earth debate team, and boy, it was an experience. We were trying to talk about the sextant and celestial navigation, and they seemed to be rather hung up on the fact that they seem to believe that in order to have refraction in the atmosphere, you have to know the value of the radius of the Earth. Now, even though I never mentioned the radius of the Earth, I never put any measurements down for the radius of the Earth, and I never used the radius of the Earth in any way, shape, or form, he got stuck on this. And the constant screams of, "Where'd you get R? Where'd you get R? Where'd you get R?" just came up like a chorus from these people. So, let's find out where we get R. How do we verify the radius of the Earth? Let's go ahead and have a look. So cue up the music, and let's have a look at how we verify the radius of the Earth. Probably the very best way to find out if our measurements of the radius of the Earth are accurate or an artifact of the mathematics is to measure it in a number of different ways and see if all of the answers come back to approximately the same thing. Well, let's go ahead and have a quick look at the ways that we traditionally measure the radius of the Earth. The first one, obviously, was Eratosthenes, where we looked at the shadow of a stick in Alexandria and compared it to vertical sunlight in Syene. We found that it was 7.2 degrees, which was the zenith angle, and the distance between the two locations was 500 miles. That gave us a circumference of roughly 25,000 miles, and it's child's play to determine the radius from that. You simply divide it by 2 pi. Next came Al-Biruni, and Al-Biruni measured the radius directly by measuring the dip angle from the top of a mountain to the horizon. Here's the mathematics that he used. This is the classic Al-Biruni formula. Height of the mountain times the cosine of that dip angle over 1 minus the cosine of the dip angle equals the radius. We've derived this in other videos. I'm not going to do it again now. Now, recently I came up with my own method for deriving the radius of the Earth directly, and thanks to Blue Marble Science, it has acquired the name, the method Al-Biruni. Now, what I did with that was I looked at the distance to an object and the height of the object that was hidden from my view. And what I found was that if you took the distance and squared it, subtracted the hidden height squared, and divided it by 2 times the hidden height, you came up with the radius of the Earth. Now, the accuracy of a sextant in the hands of an amateur, even a talented one like me, is considered about 15 nautical miles. So you can find your position reliably within 15 nautical miles. I regularly do much better than that. But say here in northern Michigan, I didn't account for refraction at all. Now, that's one of the normal corrections that you would make on your site, but say I just ignored refraction. How much would that change my position? About 0.8 of a mile. Now, given the size of the Earth, that really isn't all that bad. The only reason we do correct for refraction, especially in sightings high in the sky rather than down on the horizon, is we want to just add that much more accuracy. Now, with my method, the method Al-Biruni, I'm looking at the hidden height of an object right on the horizon. Now, the problem with that is that refraction becomes very significant right on the horizon. Now, under standard conditions, I find that I have to divide this number by about 1.22 in order to account for that refraction and get the true radius of the Earth. And that's very consistent over numerous readings. But then again, refraction is extremely variable. And of all of the methods here, that is probably the least accurate, but it's probably one of the easier ones to do, and it gives you a very reasonable result. But anytime you're dealing with an optical measurement of something, you run into problems, because you do have refraction and atmospheric variability. However, there's another way that we can measure the radius of the Earth, and that is by measuring distance across the ground. We can accurately measure distance across the ground. I don't think that there is any question that we can do that. We do this on roads. We do this on aircraft flight paths. For example, we know that the distance between Chicago O'Hare Airport and Sky Ranch Airport in Phoenix, Arizona is 1,251 nautical miles. There's no refraction involved in that. It's a measured distance. So how would we determine the radius of the Earth from that information? We're going to use something called the Haversine formula. Let's go over that real quick. Okay, so let's go ahead and have a look at the schematic of this problem. I find drawing a picture is very easy for me to understand, and hopefully that'll help you some too. So here is Chicago O'Hare. It's located at 41.98 degrees north, 87.91 degrees west. Here is Phoenix. It's at 33.45 north and 112.07 degrees west. So if you were to subtract the difference between that latitude and that latitude, you would come up with 8.53. If you were to find the difference between this longitude and that longitude, it would be 24.16 degrees. Now again, this is a right triangle. It would be longer than this. I just have it shortened up a little bit for illustration. Now on a flat surface, using the Pythagorean theorem, all we would have to do is square that number and square that number, add them together, and we would get that number squared, which is the direct distance between Chicago and Phoenix. Let's go ahead and do that real quick. Now, if we square 8.53 and add it to the square of 24.16, we're going to come up with 25.62. Now, each degree on the surface of the Earth is 60 nautical miles. So we take 60 and multiply it by 25.62, and we come up with 1537 nautical miles between Chicago and Phoenix. That is the only way that this can occur on a flat Earth. It must be that distance. However, that's not the distance between the two. The distance between those two airports, according to any reference that you want to look at, is 1,251 nautical miles. So why is that? It's because the Earth is not flat. That absolutely proves it right there. This absolutely rules out the possibility that the Earth can be flat. So, how do we find that number? Well, let's assume for a moment that it's a sphere. We're going to use something called the Haversine formula. Let's go over that real quick. Now, let's go back to our unit circle really quick. So, a unit circle is a circle of radius 1. Now, we have an angle here. We'll call that angle alpha. Now, as we recall from Trig on Tuesday, this side is the cosine. This side is the sine. Now, most of the time we talk about 6 main trigonometric functions. We have the sine, the cosine, the tangent, and then we have their reciprocals, which are called the cosecant, the secant, and the cotangent. However, those are not the only trigonometric functions. So, for example, look at this segment right here. If you knew the length of that segment, it would tell you the difference in distance across the surface of the Earth compared to a chord of an angle. And as you recall, the chord of an angle, say this whole angle here, is equal to 2 times the sine of half the angle. In this situation, if we were looking at this chord, here is the whole angle that that chord would encompass. Angle alpha would be 1/2 the angle. And if we took the sine of angle alpha and multiplied it by 2, we would have the length of this chord. One of the ways that they used to be able to calculate the distance across the surface of a sphere was to use this segment right here. And this segment is called the versine. Sometimes you may hear it referred to as sagitta, which means in Latin the arrow, and I think that you can see why they call that an arrow. But in this video, we're going to refer to it as the versine. Now, the formula for a versine is the sine of the angle squared. But wait, there's more. we're not going to really talk about the versine. If you were to take this angle out, and just talk about the original angle alpha and that full versine, this now would be the versine of half the angle, and that has a special name. It's called a haversine. And the formula for a haversine is the sine square of the angle divided by 2. Well, let's see how the haversine is used to determine a great circle distance, which is what we're talking about here. It's the shortest distance between any 2 points on the surface of the Earth. If we had an airport up here, and we wanted to go to an airport here, it would be a rather simple matter of just multiplying angle alpha by 60. Now, the thing about the haversine is that you're measuring the haversine of half the angle, half this angle alpha. So once we have that, we have to multiply it by 2. So here's how you find the distance. You take 2 times the radius of the sphere times the square root of the haversine. Now, why not just take the number of degrees and multiply it by 60? And we can do that if we're calculating distances that go along the same line of longitude, because all lines of longitude are great circle distances. So any 2 locations along that line of longitude, if you just multiply the distance in degrees by 60 nautical miles, you have the distance between them. But what happens if instead of being here on this line of longitude, we literally swing this out to a different degree of longitude? Now we have to find a distance between these 2 points. And that's a little bit more complicated. Let me show you the formula for that. Now, that formula may look a little bit intimidating, but if you think about it, it really isn't all that difficult. This first part right here, that is the haversine between the starting latitude and the ending latitude. That forms a triangle on the surface of the Earth, and there's a distance between those 2 points, essentially going along the same line of longitude. Now, likewise, if we were just going up and down, that would be easy. But if we're going down and over, that changes the length of the segment connecting the ends of those 2 triangles. So we have to take that into account. That's why you see right here, you have the haversine of the change in longitude as well. You also have to take the cosine of the starting latitude, the ending latitude, and then you multiply it by the haversine of the change in longitude. Well, here, the change in latitude is going to be 8.53 degrees. That's basically 41.98 minus 33.45. The change in longitude will be 112.07 to 87.91. And that comes out to 24.16. So now we have our numbers there. What about these numbers here? Well, lat 1 is 41.98. Whoops, well, lat 1 is 41.98. And lat 2 is 33.45. Okay, so let's go ahead and shoot the math. Well, this term right here, if you take the sine of half of 8.53 and square it, you're going to get 0.00553. To that, we're going to add the cosine of 41.98, which is 0.743, times the cosine of 33.45, which is 0.834, times the haversine, which is going to be 0.0438. Now, if we bring this all together, we come up with 0.0326. We take the square root of that, we multiply it by 2, and the radius of the Earth in nautical miles, which is 3440. What do we get? We get 1, 2, 4, 4 nautical miles. We're 7 nautical miles off. And that can be accounted for with rounding errors. The Haverson formula accounts for a perfectly spherical Earth. And the Earth, as you know, is not perfectly spherical. It's squashed very slightly, and it's about 28 miles wider than it is tall. So that'll set up a slight error. But to be honest with you, we're within 7 miles of the airport. That's within sight of it. That's pretty good. The correct answer, which is 1251, is much closer to this number than it is to that one. And as a result, that confirms that our model, which is a spherical Earth, is much closer to reality than any flat plane. Well, let's finish you off with an exercise that you can do at home. The Detroit Metro Airport is located at 42.81 degrees north, 83.08 degrees west. North Florida Beaches Airport in Panama City Beach, Florida, is located at 30.16 degrees north, 85.66 degrees west. If you find the square root of the Haverson and multiply it by 2, the answer is going to be 0.223. The true distance between those 2 points, the known distance, is 885 statute miles. Now, as you recall from the Haverson formula, there is no mention of radius anywhere in that formula. There's no mention of radius in any of these degrees. There's no radius there. There's no radius there. Now, if you calculate the distance by the Haverson formula, d will equal 2 times the radius of the square root of the Haverson. Okay? Rearranging that a little bit and dividing the distance by twice the square root of the Haverson, and I've given you the value of this term, which is 0.223, you can find the radius of the Earth. Now, the true distance between those 2 points is measured at 885 miles. We divide that by 0.223, and we should come up with the radius of the Earth. Let's see how well it agrees with our other radiuses of the Earth. The 5 significant digits, which is being a little generous, I get 3968.6. The true radius of the Earth is 3959, so we are 9.6 miles off, simply by looking at the distance between 2 points on the Earth and using the Haverson equation. We came up with the radius of the Earth, and that compares favorably with Eratosthenes and the people like myself in Blue Marble Science and B-Ball for Life that have done the Eratosthenes experiment recently. That's the same radius that we got. It's the same radius that we get from Al-Biruni. It's the same radius we get by looking at the amount of hidden height of a building on a standard refraction day. And now it's the same distance that we get from measuring distance over the ground. Now, what I would do if I were you would be to go ahead and pick 2 airports on a north-south road near your home. For example, in my area, I can pick the airport in Gaylord, Michigan, and Capital City Airport in Lansing, Michigan. They're almost due north and south of each other. I can measure that distance with my car driving straight up 127 because it connects both of them. And I'll take my odometer reading and I'll divide it by 2 times the square root of the Haverson, and I should come up with the radius of the Earth. Why don't you try it? Well, folks, I hope you enjoyed that as much as I did. The Haverson formula looks intimidating at first, but if you use it a couple of times, it really isn't all that bad. I do it on the slide rule all the time, and I get pretty good results. Now, even though this was really a response to a nothing complaint by the Flat Earth, they like to talk about refraction, they like to talk about the radius of the Earth, I decided to just go ahead and humor them a little bit. You want to know how we got the radius of the Earth? Here's how we got the radius of the Earth. And by the way, refraction with a sextant, because you're looking up is not really all that much. The refraction really comes into play when you're down by the horizon. And as I said, if I hadn't accounted for refraction in my sextant readings, I only would have been 0.8 of a mile off. I can live with that. Can you, Nathan? Because with or without refraction on a sextant and celestial navigation, the Earth's still a globe. Now we've thoroughly proven the fact that 1, the Earth has a consistent radius no matter how you measure it, and 2, it is a physical impossibility for the Earth to be flat, given our ability to measure distances between 2 points on the Earth and the fact it doesn't match up with a flat Earth. I think it's a good time for you to start throwing yourself into a different conspiracy, Nathan, because this one here is pretty well cooked. This is Bob the Science Guy signing out from Northern Michigan. Take care, everyone, and stay healthy.